Welcome to Sleepy Science, student, where we explore the wonders of our planet one gentle breath at a time. Tonight, we're going on a slow, peaceful journey into the heart of Earth itself to discover how mountains form. These towering giants that touch the clouds, that stand silent and majestic across continents, each one telling a story that spans millions upon millions of years. I hope this video isn't too interesting. Though, if it does happen to keep you awake, at least you'll be learning something fascinating about the slow, powerful heartbeat of our planet. Not the worst way to spend a sleepless night. Before we drift into the world of tectonic forces and rising peaks, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this sleepy little channel grow and means more curious minds can find their way here to learn and rest. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in Denver at midnight, surrounded by the Rocky Mountains themselves, or listening from a flat in Amsterdam at 3 in the afternoon while pretending to work on something else entirely? Let me know in the comments. It's always such a joy to see this gentle community scattered peacefully across the globe. Now, settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you like a soft breeze drifting down from a distant mountain peak. And as we begin this gentle voyage into the forces that shape our world, remember this video is for educational and relaxation purposes only. It's not intended as medical advice, geological counseling, or a substitute for actual mountain climbing, though it's considerably safer than the real thing. Ready? Let's begin. The sleeping giants. Let's talk about what a mountain really is. When you think of a mountain, you might picture snow-capped peaks piercing the sky, or perhaps rocky cliffs dropping dramatically into valleys below. But a mountain is more than just a large pile of rock. It's a monument to patience, a testament to forces so vast and slow that they operate on timescales almost beyond human comprehension. Mountains are Earth's way of reaching upward, of expressing the restless energy that churns deep within our planet's interior. A mountain, in the simplest terms, is an elevated portion of Earth's crust that rises significantly above the surrounding terrain. Geologists generally consider anything that rises more than about 300 meters above its surroundings to be a mountain, though this definition is wonderfully flexible. Some mountains stand alone, solitary sentinels watching over plains. Others gather together in ranges, like old friends, holding hands across the landscape, stretching for hundreds or even thousands of kilometers. But here's where things get quietly interesting. Mountains aren't static. They're not permanent fixtures carved once and left to stand forever. Mountains are constantly changing, constantly in motion, though that motion is so slow that it becomes invisible to human eyes. Right now, as you lie there, the Himalayas are growing, the Alps are rising, the Rockies are being worn down. It's a gentle dance between creation and destruction, played out over millions of years. You can think of mountains like old trees in a forest. They grow slowly, reaching upward toward the sky. They weather storms, they age. Eventually, they erode away, returning their substance to the earth. But unlike trees, mountains measure their lifespans, not in decades or centuries, but in millions of years. A mountain range that seems eternal to human civilization might be, in geological terms, remarkably young. Right now, somewhere on Earth, new mountains are being born. Somewhere else, ancient peaks are being slowly dismantled by wind and water. The planet is always reshaping itself, always sculpting new features, always writing new chapters in its geological story. And we, in our brief human lifetimes, catch only the tiniest glimpse of this endless transformation. The tallest mountain on Earth, Mount Everest, stands about 8,849 meters above sea level. That's nearly 9 kilometers of rock and ice, reaching into the thin upper atmosphere. If you were to climb Everest, which I certainly don't recommend at this hour, it would take weeks of preparation, acclimatization, and effort. Yet this mountain, this enormous pile of rock, was once at the bottom of an ancient sea. The limestone near its summit contains fossils of marine creatures that lived hundreds of millions of years ago. How does ocean floor become the roof of the world? That's exactly what we're here to explore. Mountains shape more than just landscapes. They influence weather patterns, creating rain shadows and forcing air masses to rise and cool. They serve as barriers between cultures and climates, dividing ecosystems and creating unique habitats found nowhere else on Earth. They capture imagination and inspire awe. Throughout human history, mountains have been considered sacred, feared, worshipped, and conquered. They've been seen as homes of gods, as challenges to overcome, as boundaries that define nations. Let's pause for a moment and consider the sheer variety of mountains. Some are jagged and sharp, their peaks cutting the sky like broken teeth. Others are rounded and gentle, worn smooth by time and weather. Some mountains are volcanic, born from fire and ash. Others are folded sedimentary rock, layers of ancient seafloor compressed and lifted. Each mountain has its own personality, its own story, its own way of standing against the sky. The thing about mountains is that they're patient. They don't rush. A mountain doesn't care about human timelines, about our calendars and clocks. Mountains operate on geological time, where 1,000,000 years is barely a moment. This patience is, in a way, quite soothing. While we humans worry about deadlines and appointments, mountains simply exist, changing so slowly that the change becomes invisible, reminding us that some things transcend our hurried little lives. Scientists estimate that there are over 1,000,000 mountains on Earth, ranging from modest hills to towering giants. They exist on every continent, even Antarctica, where the transantarctic mountains stretch across the frozen landscape. Mountains rise from the ocean floor as seamounts and volcanic islands. They cluster into vast ranges and stand alone as isolated peaks. Everywhere you look on Earth's surface, if you look carefully enough, you'll find evidence of vertical motion, of Earth's crust being pushed and pulled and folded into new shapes. But here's a curious thing. Not all mountains form the same way. Just as there are many ways to build a house, there are many ways to build a mountain. Some mountains are pushed up from below by rising magma. Some are squeezed upward when tectonic plates collide. Some form when blocks of crust are lifted along fault lines. Each method creates mountains with different characteristics, different shapes, different stories to tell. Imagine Earth's crust as a puzzle made of massive pieces, floating on a layer of softer, partially molten rock. These puzzle pieces, called tectonic plates, are constantly moving, driven by heat from Earth's interior. Where these plates meet, interesting things happen. Sometimes they collide. Sometimes they slide past each other. Sometimes one dives beneath another. And wherever these interactions occur, mountains often rise. The formation of mountains is, fundamentally, a story about energy. Deep inside Earth, heat from radioactive decay and residual warmth from the planet's formation creates convection currents in the mantle, that thick layer of rock between the crust and the core. These currents move slowly, like honey warming on a countertop, and they drag the tectonic plates along with them. This movement, this constant restless shifting, provides the energy that builds mountains. It's worth noting that mountains don't form in isolation. The same forces that create mountains also trigger earthquakes, build volcanoes, and reshape entire continents. Mountain building is part of a larger system, a planetary machine that recycles rock, moves continents, and continuously renovates Earth's surface. If Earth were a static planet, dead and unchanging like the moon, there would be no mountains. Mountains are proof of our planet's inner fire, its geological vitality. So as we lie here, comfortable and still, mountains around the world are doing their patient work. They're rising, imperceptibly slowly. They're eroding, grain by grain. They're shaping weather, creating habitats, inspiring wonder. And to understand how they do this, we need to travel deep into Earth's interior to explore the forces that move continents and push rock toward the sky. But we'll do that slowly, gently, one concept at a time. The restless planet. Let's drift down into the Earth now, below the mountains, below the soil and rock, deep into the interior of our planet. If you could somehow journey to the center of Earth, an impossible trip but pleasant to imagine, you'd travel about 6,400 kilometers through increasingly hot and dense layers. You'd pass through the crust, that thin outer skin where we live and where mountains form. You'd continue through the mantle, a thick layer of hot, slowly flowing rock. Eventually, you'd reach the core, a ball of iron and nickel, the outer part liquid, the inner part solid, spinning and generating Earth's magnetic field. But it's the mantle we're most interested in tonight, because the mantle is where the action happens. The mantle isn't quite liquid and isn't quite solid. It exists in a state called plastic, which means it can flow, but only very, very slowly. Think of it like pitch or very thick honey. If you were patient enough, and mountains certainly are, you could watch the mantle flow, churning in massive convection cells driven by heat from below. Here's how it works, and it's rather elegant when you think about it. Heat from Earth's core and from radioactive decay within the mantle warms rock from below. This hot rock becomes slightly less dense, and like hot air rising on a summer day, it begins to rise toward the surface. As it rises, it cools, becomes denser, and eventually sinks back down. This creates a circular motion, a convection current, much like you might see in a pot of gently simmering soup. These convection currents are immense. They're hundreds of kilometers wide and move at the breathtaking speed of a few centimeters per year. That's about as fast as your fingernails grow. Yet despite their slowness, these currents have enough force to move continents, to build mountains, to reshape the entire surface of the planet. It's a reminder that gentle, persistent forces, given enough time, can accomplish extraordinary things. Now, floating on top of this slowly churning mantle is Earth's crust, broken into about 15 major tectonic plates and several smaller ones. These plates include continents and ocean floor, massive rafts of rock drifting on the plastic mantle below. Some plates are enormous. The Pacific plate covers about 103 million square kilometers, roughly a fifth of Earth's surface. Other plates are smaller, squeezed between their larger neighbors. The plates don't stay still. They can't. The convection currents in the mantle below drag them along, push them together, pull them apart. Some plates move faster than others. The fastest moving plate, the Cocos Plate near Central America, moves about 90 millimeters per year. That's still just slightly faster than your hair grows, but in geological terms, it's positively racing. Other plates move more slowly, barely crawling along at a few millimeters per year. You can think of the tectonic plates like ice flows on a slowly moving river. They drift, they collide, they crack apart. Where two plates meet, you find plate boundaries, and these boundaries are where most of the exciting geological action occurs. It's at plate boundaries that earthquakes rumble, volcanoes erupt, and mountains rise. The plates themselves might seem calm, stable, but their edges are restless and dynamic. There are three main types of plate boundaries, and each one creates mountains in different ways. Let's explore them gently, one at a time, allowing each concept to settle before moving to the next. First, there are divergent boundaries, where plates move apart. Imagine two ice flows drifting away from each other, leaving a gap of open water between them. At divergent boundaries, as the plates separate, hot magma rises from the mantle to fill the gap, creating new crust. This mostly happens on the ocean floor, at features called mid-ocean ridges. While these underwater mountain ranges are fascinating, they're not the towering peaks we typically think of when we picture mountains. But they're important because they show that Earth is constantly creating new crust, new rock, new terrain. Second, there are convergent boundaries, where plates move toward each other. This is where things get interesting for mountain building. When two plates collide, something has to give. Rock has to go somewhere. And depending on what types of crust are colliding, whether it's oceanic crust or continental crust, different things happen. We'll explore this in much more detail soon, because convergent boundaries are responsible for Earth's most spectacular mountain ranges. Third, there are transform boundaries, where plates slide past each other horizontally. Picture two ice flows grinding alongside each other, edge to edge. The San Andreas Fault in California is a famous transform boundary, where the Pacific Plate slides past the North American Plate. Transform boundaries create earthquakes and can produce some uplifted terrain, but they're not the primary mountain builders. They're the sliding doors, while convergent boundaries are the colliding cars. Now, let's pause for a moment and consider how remarkable this all is. The ground beneath us, which feels so solid and permanent, is actually floating on a layer of slowly flowing rock. The continents we live on are drifting, carrying us along at speeds measured in millimeters per year. The mountains we see as eternal are actually temporary features, pushed up by plate collisions and destined eventually to be worn away. Earth is not a static ball of rock. It's a dynamic, living system, constantly in motion, constantly changing. The theory that explains all of this, plate tectonics, is relatively young as scientific theories go. It wasn't until the 1960s that scientists fully understood how Earth's surface moves and changes. Before that, people noticed that the coastlines of Africa and South America seemed to fit together like puzzle pieces, but they couldn't explain how continents might move. The idea seemed absurd. How could massive continents drift across the planet? But slowly, evidence accumulated. Scientists discovered that the magnetic orientation of rocks on either side of mid-ocean ridges mirrored each other, suggesting the rocks had formed at the ridge and then moved apart. They found ancient climate indicators in places where the climate made no sense: glacial deposits in Africa, coal forests in Antarctica, suggesting the continents had once been in different positions. They measured the age of ocean floor and found that it was youngest at the ridges and oldest near the continents, exactly what you'd expect if new crust was constantly forming and spreading. When plate tectonics was finally accepted, it revolutionized geology. Suddenly, everything made sense. Earthquakes, volcanoes, mountain ranges, they all fit into a unified theory of how Earth works. It was like finding the instruction manual for a complex machine you'd been trying to understand for centuries. And it all comes back to heat, to convection, to the restless energy of our planet's interior. Alfred Wegener, a German meteorologist and geophysicist, was one of the early proponents of continental drift. In 1912, he proposed that all continents had once been joined together in a supercontinent he called Pangaea. His evidence included matching rock formations across different continents, similar fossil species found on opposite sides of oceans, and the puzzle piece fit of coastlines. But Wegener couldn't explain the mechanism, how continents could move. The scientific community largely rejected his ideas during his lifetime. It wasn't until decades after his death that seafloor spreading and plate tectonics provided the explanation he lacked. The story of plate tectonics is a reminder that science progresses slowly, sometimes painfully. Good ideas can be rejected if they're too far ahead of their time, or if they lack supporting evidence. But truth has a way of emerging eventually, gently but persistently, like mountains rising from the earth. Wegener's ideas were vindicated, though he never lived to see it. And now we understand that his vision of moving continents was fundamentally correct, though the details were more complex than he imagined. So here we are, lying comfortably in bed, while beneath us the planet slowly churns and shifts. The tectonic plate we're on is moving right now, though we can't feel it. Somewhere, plates are colliding, mountains are rising. Somewhere else, plates are spreading apart, creating new ocean floor. It's all happening at a pace too slow for human perception, but it's happening nonetheless. And over millions of years, these tiny incremental movements add up to enormous changes. Mountains, then, are symptoms of this larger planetary process. They're the surface expression of forces operating deep below. When you look at a mountain range, you're seeing the result of tectonic plates pushing against each other with the weight and force of entire continents. You're seeing what happens when unstoppable forces meet immovable objects over timescales that span millions of years. And somehow, that's rather peaceful to contemplate. The mountains are patient. The planet is patient. And we, for this moment, can be patient too. Section 3. When plates collide, continental collision. Now we move to the heart of mountain building, to the collision zones where tectonic plates come together. This is where the most spectacular mountains form, where continents collide and rock is forced upward, reaching toward the sky. It's a process called orogeny, from the Greek words for mountain and genesis, the birth of mountains. And like all births, it's a dramatic, transformative event, though one that unfolds in ultra-slow motion. Let's start with the most spectacular type of collision. When two continental plates come together. Continental crust, remember, is light and buoyant, made primarily of granite-type rocks. When two continents collide, neither plate wants to sink into the denser mantle below. Neither can subduct. So what happens? They crumple, they fold, they push against each other like two cars in a very slow-motion collision, and the crust between them buckles upward. This is how Earth's highest mountains form. The Himalayas are the most spectacular example of this type of collision. About 50 million years ago, which is recent in geological terms, the Indian plate, carrying the Indian subcontinent, began colliding with the Eurasian plate. India had broken away from the ancient supercontinent Gondwana and drifted northward across what is now the Indian Ocean. When it reached Eurasia, there was nowhere for either plate to go. The result? The crust crumpled and thickened, pushing upward to form the Himalayan mountain range. This collision is still happening. India continues to push northward at a rate of about 50 millimeters per year. The Himalayas continue to rise, though erosion wears them down at nearly the same rate. Mount Everest, the highest point on Earth's surface, grows by about 4 millimeters each year. That's slower than your fingernails grow, but over geological time, it adds up. Over the past 50 million years, rocks that once lay at sea level have been lifted nearly 9 kilometers into the sky. Let's pause here and consider what this means. The collision between India and Eurasia has literally changed the face of the planet. It's created the Tibetan Plateau, a vast elevated region the size of Western Europe, with an average elevation of over 4,500 meters. This plateau has been called the roof of the world, and it's the largest and highest plateau on Earth. It's altered atmospheric circulation patterns, affecting monsoon systems and climate across Asia. It's created habitat for unique species found nowhere else on Earth. And it's given us the highest mountains in the world, peaks that have drawn explorers and mountaineers for generations. You can think of the collision between tectonic plates like folding a tablecloth. If you push two edges of a tablecloth toward each other on a table, the cloth in the middle buckles and folds, forming ridges and valleys. This is essentially what's happening when continents collide. Layers of rock that were once flat are bent, folded, and stacked on top of each other. Sedimentary layers that took millions of years to form are compressed into tight folds in a geological eye blink. Geologists have found marine fossils high in the Himalayas, far above any ocean. These aren't fossils that flew or crawled up the mountain. They're fossils of creatures that lived and died on the ocean floor, trilobites, ammonites, ancient sea lilies, whose remains were buried in sediment, compressed into rock, and then lifted thousands of meters into the air by the collision of continents. The famous Comolangma limestone near Everest's summit contains fossils from the Ordovician period, about 450 million years old. It's a reminder that mountains are not just piles of rock. They're geological archives containing the history of ancient oceans, ancient climates, ancient life. The forces involved in mountain building are almost incomprehensible. When two tectonic plates collide, they do so with the force of entire continents behind them. The pressure is so intense that rocks that were once buried deep in the crust are squeezed and heated until they partially melt, creating metamorphic rocks. Rocks that have been transformed by heat and pressure into new forms. Limestone becomes marble. Shale becomes slate. Granite becomes gneiss. The rocks themselves are changed by the experience of mountain building. But here's something gentle to consider. Despite the enormous forces involved, the process is slow. Mountains don't burst upward overnight. They rise millimeter by millimeter, year after year, over millions of years. If you could somehow watch a mountain range forming in fast forward, it would look like the earth was breathing, the crust swelling and rising like a chest inhaling. But in real time, it's imperceptible. You could spend your entire life in the shadow of a growing mountain and never notice it getting taller. There's something almost meditative about this slowness. While we humans rush through our days, hurrying from one task to another, the planet takes its time. Mountains don't hurry. They simply rise, steadily and patiently, following the inexorable physics of plate tectonics. There's no urgency, no deadline, just the slow, continuous process of Earth reshaping itself. Other mountain ranges around the world tell similar stories of collision. The Alps formed when the African plate collided with the Eurasian plate, starting about 65 million years ago. Before the collision, there was an ocean called the Tethys Sea between the two continents. As the plates converged, the ocean gradually closed, and the sediments that had accumulated on its floor were compressed and uplifted, forming the Alps. The process continues today, with the Alps still rising at about a millimeter per year, though erosion largely keeps pace with the uplift. The Appalachian Mountains in eastern North America are the worn-down remnants of mountains that formed when the continents came together to form the supercontinent Pangaea about 300 million years ago. These ancient mountains were once as high as the Himalayas, perhaps higher, but they've been eroding for hundreds of millions of years. Today, the highest peak, Mount Mitchell in North Carolina, stands at just 2,037 meters. The Appalachians show us what all mountains eventually become: gentle, rolling hills, the mere stumps of former giants. The Urals in Russia mark the boundary where Europe and Asia collided, also during the formation of Pangaea. These mountains, like the Appalachians, are ancient and worn down. But they remind us that the distinction between Europe and Asia is, in a geological sense, arbitrary. They're the same landmass, the same continent, separated only by a line of old mountains that mark an ancient collision zone. It's worth noting that not all of a colliding plate's surface rises. As the crust is compressed, some parts are pushed down as well as up. This creates basins and valleys alongside the mountains. The crust might thicken to twice its normal depth in collision zones, with some of that material extending down into the mantle, even as the mountains rise above. It's like squeezing a pillow. Some of the filling bulges up, while some is pushed to the sides and down. In the Himalayas, the crust beneath the mountains is about 70 kilometers thick, roughly twice as thick as normal continental crust. This means that for every meter of mountain we see above the surface, there's another meter or more of root extending down into the mantle. It's this deep root that allows the mountains to float high, maintaining their elevation through the principle of isostasy, which we'll explore more deeply in a later section. The Tibetan Plateau, that vast elevated region north of the Himalayas, is actually rising faster than the mountain range itself in some places. As India continues to push into Eurasia, the force isn't just building mountains along the collision front, it's also pushing the entire plateau upward and outward. The plateau is slowly expanding, its edges moving northward and eastward. Rivers are being pushed off their courses. Ancient lake beds are being uplifted. The entire region is still responding to the collision that began 50 million years ago. So as we drift here, comfortable and relaxed, we can imagine the Himalayas slowly rising, millimeter by millimeter. We can Picture the Indian plate grinding against Eurasia, the rocks folding and breaking, the mountain peaks reaching ever higher into the thin air. It's all happening right now, has been happening for 50 million years, and will continue for millions of years to come. The mountains are patient teachers, reminding us that even the mightiest changes occur slowly, steadily, gently. When plates collide. Subduction zones. Let's turn our attention now to a different type of plate collision, one that occurs when an oceanic plate meets a continental plate. This is the realm of subduction zones, places where one plate slides beneath another, diving down into the mantle in a process that's as elegant as it is powerful. Subduction zones build some of Earth's most dramatic mountain ranges and create some of our most active volcanoes. Here's what happens. Oceanic crust is made primarily of dense basalt rock, formed at mid-ocean ridges where magma wells up from the mantle and solidifies. Continental crust, by contrast, is made of lighter granite-type rocks. When these two types of crust collide, the denser oceanic plate naturally sinks beneath the lighter continental plate. It's a bit like sliding one piece of paper under another, except these pieces of paper are tens of kilometers thick and thousands of kilometers wide. As the oceanic plate descends into the mantle, several fascinating things happen. The increasing temperature and pressure cause water trapped in the oceanic crust to be released. This water comes from minerals in the rock itself and from seawater that had seeped into cracks and pores in the oceanic crust. As this water rises into the wedge of mantle above the subducting plate, it lowers the melting point of the mantle rock. Partial melting occurs, creating magma that's less dense than the surrounding rock. This buoyant magma rises through the overlying continental crust, sometimes erupting at the surface to form volcanoes, sometimes solidifying underground to form large bodies of granite called batholiths. The Andes Mountains in South America provide a beautiful example of this process. The Nazca Plate, carrying oceanic crust, is subducting beneath the South American plate at a rate of about 70 millimeters per year. As it does, it creates a chain of volcanoes along the western edge of the continent. These volcanoes, combined with the compression and uplift of the continental crust, have built a mountain range that stretches for about 7,000 kilometers, the longest continental mountain range on Earth. And it's still growing, still building, rising a few millimeters each year. Imagine standing at the base of a volcano in the Andes. The mountain before you is, in a very real sense, recycled ocean floor. Rock that once lay at the bottom of the Pacific Ocean has been dragged down into the mantle, melted, transformed, and returned to the surface in a new form. It's Earth's way of recycling, of bringing material from the depths back to the surface, of renewing and reshaping the landscape. Nothing is wasted in this system. Everything is transformed and reused in an endless cycle. Let's pause for a moment and think about the magma rising beneath a subduction zone. As it ascends through the continental crust, it heats the surrounding rock, sometimes melting it partially, incorporating it into the rising magma. The magma changes composition as it rises, becoming richer in silica and other light elements. By the time it reaches the surface, it might be quite different from the basaltic magma that originally formed from the mantle. This is how andesite forms, a type of volcanic rock named after the Andes and common in subduction zone volcanoes. Not all the magma reaches the surface. Some solidifies deep underground, forming huge bodies of granite called batholiths. These batholiths can be hundreds of kilometers long and tens of kilometers thick. They're like frozen magma chambers, capturing a moment in the mountain building process. Over millions of years, erosion may remove the overlying rock, exposing these ancient magma chambers at the surface. The Sierra Nevada in California is actually a huge batholith, granite that formed deep underground during an ancient subduction zone and was later exposed by erosion and uplift. The Cascade Range in the Pacific Northwest of North America is another subduction zone mountain range, though it's much younger and less extensive than the Andes. Here, the Juan de Fuca plate is subducting beneath the North American plate. The result is a chain of volcanoes: Mount Rainier, Mount St. Helens, Mount Hood, Mount Shasta, each one a testament to the subduction process. Some of these volcanoes are active, erupting periodically. Mount St. Helens famously erupted in 1980, demonstrating that these mountains are very much alive, still growing, still capable of dramatic change. But subduction zones don't just create volcanoes, they also create earthquakes, some of the largest and most destructive earthquakes on Earth. As the oceanic plate slides beneath the continental plate, it doesn't move smoothly. Friction locks the plates together. Stress builds up over decades or centuries. Eventually, the stress exceeds the friction, and the plates suddenly slip, releasing energy in an earthquake. The 2010 Chile earthquake, the 2011 Tohoku earthquake in Japan, the 1960 Great Chilean earthquake, the largest earthquake ever recorded, all occurred in subduction zones. These earthquakes contribute to mountain building in a direct way. Each earthquake along a subduction zone typically uplifts the continental plate by a small amount, perhaps a meter or two. Over millions of years and countless earthquakes, this incremental uplift adds up to thousands of meters of elevation. Mountains, in this view, are built by earthquakes, one sudden jolt at a time, punctuated by long periods of quiet stress accumulation. Let's think gently about what's happening deep beneath a subduction zone. The oceanic plate, which formed at a mid-ocean ridge perhaps 100 million years ago, has traveled thousands of kilometers across the ocean floor. It's accumulated a layer of sediment, the remains of microscopic organisms that lived in the ocean, settling slowly to the seafloor over millions of years. Now, this plate is being dragged back into the mantle, recycled. Some of the sediment is scraped off and accreted to the edge of the continental plate, forming what geologists call an accretionary wedge. But some is carried down with the subducting plate, eventually to be melted and incorporated into new magma. The subducting plate can be traced hundreds of kilometers down into the mantle using earthquake waves. Earthquakes occur along the sinking slab as it bends and breaks under stress. By mapping these earthquakes, seismologists can create a picture of the subducting plate's shape and position. In some places, like beneath Japan, the slab descends steeply. In others, like beneath parts of South America, it descends at a shallow angle, traveling hundreds of kilometers horizontally beneath the continent before descending into the deep mantle. What happens to the subducted plate eventually? Does it melt completely? Does it sink to the bottom of the mantle? Scientists are still working out the details, but it appears that some subducted material does reach the core mantle boundary, about 2,900 kilometers down. There, it may pool for a while before being incorporated into mantle convection and eventually rising again. The cycle is complete. Oceanic crust forms at mid-ocean ridges, travels across the ocean floor, subducts at trenches, sinks through the mantle, and eventually rises again to form new oceanic crust. The timescale for this entire cycle might be 200 to 300 million years. Not all subduction zones are the same. Some, like the Cascadia subduction zone beneath the Pacific Northwest, are relatively quiet, accumulating stress over centuries and releasing it in rare but massive earthquakes. Others, like the subduction zones around the Ring of Fire encircling the Pacific Ocean, are continuously active, with frequent earthquakes and volcanic eruptions. Each subduction zone has its own personality, its own rhythm, its own way of building mountains and reshaping the landscape. So as we lie here, relaxed and comfortable, we can think of the subduction zones around the world, quietly doing their work. Oceanic plates sliding beneath continents, water being released from descending slabs, magma forming and rising, volcanoes building their cones, earthquakes shaking the ground and lifting mountains a bit higher. It's all part of the same system, the same planetary machine that's been operating for billions of years and will continue for billions more. The mountains built by subduction are different from those built by continental collision, but they're equally impressive, equally patient, equally persistent in their slow rise toward the sky. Volcanoes and fire mountains. Let's turn our attention now to a different kind of mountain, one born not from collision but from fire. Volcanic mountains are mountains built by magma rising from Earth's interior, erupting at the surface, and piling up layer after layer of lava and ash until a cone-shaped peak stands where once there was flat ground. These are some of Earth's most dramatic and beautiful mountains, and they form through a process quite different from the collision-driven peaks we've been discussing. Volcanoes can form in several different settings, but let's start with the one we've already touched upon: subduction zones. Remember how oceanic crust slides beneath continental crust, releasing water that causes partial melting in the mantle above? That magma has to go somewhere. It rises through the overlying crust, taking the path of least resistance, following cracks and weaknesses in the rock. Sometimes it reaches the surface and erupts, building a volcano. The volcanoes that form at subduction zones tend to be steep-sided and cone-shaped, built from alternating layers of lava and ash. Mount Fuji in Japan is perhaps the most iconic example, its perfect symmetrical cone rising from the landscape like a geometric dream. The mountain has been celebrated in Japanese art and poetry for centuries, a symbol of beauty and permanence. Yet Mount Fuji is actually quite young, having formed about 100,000 years ago. It last erupted in 1707, and it will certainly erupt again, adding new layers to its graceful cone. Mount Rainier in Washington state is another impressive stratovolcano, the technical term for these layered fire mountains. Standing 4,392 meters tall, it dominates the Seattle skyline on clear days. The mountain is covered by more glaciers than any other peak in the contiguous United States, about 35 square kilometers of ice. These glaciers are remnants of larger ice sheets that once covered the region during the last ice age. As climate warms, the glaciers are slowly shrinking, changing the mountain's appearance and hydrology. These subduction zone volcanoes often form chains or arcs, following the curve of the plate boundary. The ring of fire around the Pacific Ocean is actually a ring of subduction zones, places where oceanic plates are diving beneath continental plates or other oceanic plates. And all around this ring, volcanoes stand like sentinels, marking the boundaries between tectonic plates. The ring includes the Cascades in North America, the Andes in South America, the volcanoes of Japan, Indonesia, the Philippines, and New Zealand. It's a reminder that Earth's interior is still hot, still active, still capable of producing dramatic change. But there's another way volcanic mountains form, one that's even more intriguing. Sometimes, magma rises from deep in the mantle, punching through tectonic plates like a blowtorch through thin metal. These are called hotspots, and they create volcanic mountains in places far from any plate boundary. The Hawaiian Islands are the most famous example of hotspot volcanism, a chain of volcanic islands rising from the middle of the Pacific Plate, thousands of kilometers from the nearest plate boundary. Here's how it works, and it's wonderfully elegant. Deep in the mantle, perhaps at the boundary between the mantle and the core, a plume of especially hot rock rises toward the surface. This mantle plume is like a column of heat, a geological blowtorch pointed at the base of the crust. Where the plume reaches the crust, partial melting occurs, and magma rises to the surface, erupting and building a volcano. But here's the clever part. The tectonic plate above the hotspot is moving. The mantle plume stays relatively fixed in place, but the plate drifts over it like a piece of paper moving over a candle flame. So the hotspot burns a hole through the plate, building a volcano. Then the plate moves, carrying that volcano away from the hotspot. The volcano becomes extinct as it moves away from its heat source. Meanwhile, a new volcano begins to form over the hotspot. Over millions of years, this creates a chain of volcanoes, each one progressively older as you move away from the active hotspot. The Hawaiian Islands perfectly illustrate this process. The big island of Hawaii, at the southeastern end of the chain, is the youngest and most volcanically active. Kilauea and Mauna Loa, two of the most active volcanoes on Earth, are currently positioned over the Hawaiian hotspot. Kilauea has been erupting almost continuously since 1983, though the style and location of eruptions have changed over the years. Its lava flows have added hundreds of acres of new land to the island, literally growing Hawaii in real time. As you move northwest along the island chain, the islands get progressively older and more eroded. Maui is about 1 million years old. Oahu, where Honolulu is located, is about 3 million years old. Kauai, at the northwestern end of the main islands, is about 5 million years old and has no active volcanoes. It's being slowly worn down by erosion, its peaks rounded by time and weather, its valleys deeply carved by streams. But the Hawaiian Emperor Seamount chain doesn't stop at Kauai. It extends thousands of kilometers to the northwest, forming underwater mountains, seamounts, that get progressively older. Eventually, the chain turns sharply north, forming the Emperor Seamounts, which extend all the way to the Aleutian Trench near Alaska. The oldest volcano in this chain is about 80 million years old. It's like a geological breadcrumb trail, showing the path the Pacific Plate has taken over the hotspot during the past 80 million years. Let's pause for a moment and think about Mauna Loa. If you measure it from its base on the ocean floor to its summit, Mauna Loa is actually taller than Mount Everest. From base to peak, it's about 9,170 meters high. It just happens that most of that height is underwater. Above sea level, Mauna Loa rises 4,169 meters, respectable but not extraordinary. But consider the full mountain, and it's the largest mountain on Earth in terms of volume, containing about 75,000 cubic kilometers of rock. And Mauna Loa didn't form through plate collision. It was built, slowly and patiently, by lava flowing from the Hawaiian hotspot, layer after layer of solidified lava, piling up over hundreds of thousands of years, until a mountain rose from the ocean floor and broke the surface, creating an island. The oldest rocks on the Big Island are less than 500,000 years old. The entire island, massive as it is, has been built in a geological instant. Volcanic mountains have a different character than mountains formed by collision. They tend to be more isolated, rising from relatively flat terrain. Their shapes are often more regular, more geometric, cones and shields rather than jagged ranges, and they're active in a way that collision mountains aren't. A volcanic mountain might erupt, changing its shape in days or hours. It might grow suddenly as new lava is added to its flanks. It might collapse in a massive landslide, reshaping itself dramatically. Shield volcanoes like those in Hawaii have gentle slopes built from fluid lava that flows easily and spreads out in thin layers. The lava is basaltic, relatively low in silica, and therefore quite fluid. When it erupts, it doesn't explode violently. Instead, it flows like a river of molten rock, sometimes traveling many kilometers before solidifying. The result is a broad, gently sloping mountain that looks a bit like a warrior's shield lying on the ground. Hence the name. Stratovolcanoes like Mount Fuji or Mount St. Helens are steeper, built from thicker, stickier lava that doesn't flow as far, along with layers of ash from explosive eruptions. The lava is andesitic or rhyolitic, richer in silica, and therefore more viscous. When this type of lava erupts, gases dissolved in the magma can't escape easily. Pressure builds until the volcano explodes, sending ash and rock high into the atmosphere. These explosive eruptions build steep-sided cones, quite different from the gentle shields of Hawaii. There's something primal about volcanic mountains. They're direct connections to Earth's interior, windows into the hot molten realm below the crust. When lava flows from a volcano, you're witnessing rock from deep in the mantle making its way to the surface. That rock might have been slowly churning in convection currents for millions of years before it found its way into a magma chamber and then to the surface. Now it's cooling in the open air, solidifying, becoming part of a mountain. Volcanoes have captured human imagination throughout history. They've been feared and worshipped, seen as homes of gods or entrances to underworld realms. Vulcan, the Roman god of fire and metalworking, gave his name to these mountains. In Hawaiian tradition, the goddess Pele resides in Kilauea volcano, and eruptions are expressions of her power. In Japan, Mount Fuji is considered sacred, a dwelling place of kami, or spirits, and it's not hard to see why. A volcanic eruption is one of nature's most spectacular displays. Fountains of molten rock, clouds of ash rising into the stratosphere, glowing rivers of lava flowing down mountainsides. It's Earth's raw power on display, a reminder that our planet is not tame, not finished, not settled into any final form. But even volcanic mountains, for all their dramatic potential, spend most of their time quietly resting. Most volcanoes erupt infrequently, with years or decades or even centuries passing between eruptions. Mount Rainier last erupted about 150 years ago, and may not erupt again for another century or more. Between those moments of activity, they simply stand, weathering storms, accumulating snow, hosting life on their slopes. They're mountains first, volcanoes second, spending more time being still than being active. There are about 1,500 potentially active volcanoes on Earth, defined as volcanoes that have erupted in the past 10,000 years. Of these, about 50 to 70 are erupting at any given time, somewhere on the planet. Most of these eruptions are small, affecting only the immediate area around the volcano. But occasionally, a large eruption occurs, one that can affect climate globally by injecting ash and sulfur dioxide into the stratosphere, blocking sunlight and cooling the planet temporarily. The 1991 eruption of Mount Pinatubo in the Philippines was one such eruption. It ejected about 10 cubic kilometers of material and injected so much sulfur dioxide into the stratosphere that global temperatures dropped by about 0.5 degrees Celsius for the next 2 years. The eruption also dramatically changed the mountain itself, reducing its height by about 300 meters. In a matter of days, the volcano reshaped itself in ways that normal erosion would take thousands of years to accomplish. So as we lie here, relaxed and comfortable, we can think of the volcanic mountains scattered across the planet. Some are actively erupting right now, somewhere, Kilauea perhaps, adding new rock to the big island of Hawaii. Stromboli in Italy, which has been erupting almost continuously for thousands of years, earning it the nickname Lighthouse of the Mediterranean. Erta Ale in Ethiopia, with its persistent lava lake. Others are sleeping, dormant but not extinct, their magma chambers cooling but not yet cold. And some are extinct, their connection to the mantle severed, their fires burned out, leaving only the mountain as evidence of what once was. Each volcano, each fire mountain, a unique expression of Earth's internal heat. Folding, faulting, and breaking. Now we need to talk about what happens to rock when forces push and pull at it. Mountains aren't just lifted up as solid blocks. The rock itself bends, breaks, and deforms in fascinating ways. This is where geology becomes almost sculptural, where the earth acts like clay in the hands of a slow, patient artist. Let's explore how rocks respond to stress, and how these responses shape the mountains we see. When you apply force to rock over geological timescales, it doesn't simply stay rigid. Rock can actually bend and fold, though it does so very, very slowly. Near the surface, where temperatures and pressures are relatively low, rock tends to be brittle. It fractures and breaks rather than bending. But deeper in the crust, where temperatures are higher and confining pressure is greater, rock can behave more like a plastic material, deforming without breaking. This is called ductile deformation, and it's responsible for some of the most beautiful geological structures. Imagine taking a stack of papers and pushing on the edges. The papers buckle and fold. The same thing happens to layers of sedimentary rock when tectonic forces compress them. These layers, which were originally deposited flat and horizontal, that's the law of original horizontality, one of geology's founding principles, get bent into waves. The upward arches are called anticlines. The downward troughs are called synclines, And when you see these folds exposed in mountain cliffs, you're looking at direct evidence of the enormous forces that shaped them. Some folds are gentle and broad, stretching over kilometers. These are like rolling waves frozen in rock, with layers gently curving up and down. Others are tight and compressed, with layers bent into hairpin curves, sometimes folded back on themselves completely. In extreme cases, folds can be overturned, with upper layers actually pushed past vertical and folded back on themselves. Imagine pushing a rug on a smooth floor. Eventually it buckles and folds over on itself. The same thing happens to rock layers under extreme compression. If you were to cut through a mountain and look at its cross-section, you might see layer after layer of folded rock, like a frozen wave, a geological snapshot of tectonic forces in action. Each fold tells a story about the direction and magnitude of the forces that created it. By measuring the orientation of fold axes and the tightness of folds, geologists can reconstruct the stresses that acted on the rock, determining which direction the compressive forces came from. The Appalachian Mountains provide wonderful examples of folded rock. These ancient mountains, formed when continents collided hundreds of millions of years ago, have been deeply eroded, exposing their internal structure. From the air, you can see long parallel ridges and valleys, following the pattern of folded rocks. The ridges are made of harder rock, sandstone and quartzite, that resists erosion, while the valleys are carved into softer rock, shale and limestone, that erodes more easily. The landscape itself reflects the underlying geology, the bones of the mountain showing through its skin. In Pennsylvania, there's a feature called the Valley and Ridge Province, where you can see this pattern beautifully displayed. Parallel ridges of resistant sandstone alternate with valleys of softer shale, all following the trend of ancient folds. The pattern is so regular, so repetitive, that it looks almost artificial, like someone designed it. But it's entirely natural, the result of millions of years of erosion working on folded rock layers. But folding isn't the only way rocks respond to tectonic stress. Sometimes rocks break. When rocks fracture along a surface and the two sides move relative to each other, you have a fault. Faults are some of the most important structures in mountain building, and they come in several different varieties, each telling a different story about the forces that created them. Thrust faults occur when rocks are compressed. One block of rock is pushed up and over another block, riding up along a gently inclined fault plane. In mountain belts, formed by continental collision, thrust faults can stack multiple layers of rock on top of each other, significantly thickening the crust. The Himalayas have numerous thrust faults, with huge slabs of rock, sometimes tens of kilometers thick and hundreds of kilometers wide, pushed northward over each other as India collides with Eurasia. The main central thrust in the Himalayas is one of the most significant of these structures. It marks the boundary between the higher Himalayan crystalline rocks and the lesser Himalayan rocks below. This fault has accommodated hundreds of kilometers of displacement, with the upper plate sliding over the lower plate as the mountains formed. Even today, the fault may be active, though the current locus of deformation has shifted southward to the main frontal thrust. Normal faults, by contrast, occur when rocks are being pulled apart. One block slides down relative to the other along an inclined fault plane. While these aren't as directly involved in building mountains through compression, they're important in creating basin and range topography, where alternating mountain ranges and valleys form as blocks of crust are tilted and dropped along normal faults. The Basin and Range Province in the western United States is a classic example. Here, the crust is being stretched, extending in an east-west direction. As it stretches, it breaks along normal faults. Some blocks drop down, forming valleys or basins. Other blocks remain high or are tilted up, forming mountain ranges. The result is a distinctive landscape of parallel mountain ranges separated by flat valleys, a pattern that extends from Oregon down through Nevada and into Mexico. Strike-slip faults occur when rocks slide horizontally past each other. The San Andreas Fault is the most famous example, where the Pacific Plate grinds past the North American Plate. The fault runs for about 100 to 200 kilometers through California, from the Gulf of California to Cape Mendocino. While strike-slip faults don't directly build mountains through vertical motion, They can create uplifted areas where the fault bends or where two fault segments overlap. Let's pause here and think about what it means for rock to break. We're not talking about brittle fracture like breaking a piece of glass, though that's part of it. We're talking about enormous volumes of rock slowly, gradually sliding past each other along a fault surface. The friction between the rock faces is enormous. Imagine rubbing two pieces of sandpaper together. That's a bit like what's happening along a fault, except the sandpaper is kilometers thick and extends for hundreds of kilometers. Sometimes the fault moves smoothly in what's called creep. The motion is continuous, a few millimeters per year, accommodating the plate motion without large earthquakes. The Hayward Fault in California exhibits creep in some sections, causing gradual offsets in curbs, sidewalks, and buildings built across the fault. It's a reminder that the Earth is always moving, always adjusting, even in ways too slow to notice without careful measurement. More often, friction locks the fault until stress builds up enough to overcome it, and then the fault suddenly slips, releasing energy in an earthquake. The 1906 San Francisco earthquake was caused by slip on the San Andreas Fault, with the two sides of the fault moving up to 6 meters relative to each other in a matter of seconds. The sudden release of stored elastic energy sent seismic waves radiating out from the fault, causing widespread damage. Earthquakes are, in many ways, mountains being built in real time. Each earthquake along a thrust fault in a collision zone typically uplifts one side of the fault by a small amount, perhaps a meter or two. Over millions of years and countless earthquakes, this incremental uplift adds up to thousands of meters of elevation. Mountains, in this view, are the cumulative result of countless earthquakes, each one a small step in a long journey toward the sky. There's something almost rhythmic about this process. Stress builds gradually as tectonic plates push against each other. Friction holds the fault locked. Eventually, stress exceeds friction, the fault slips, the mountain rises a bit, and an earthquake occurs. Then the cycle begins again. It's Earth's heartbeat, slow and patient, measured not in seconds, but in decades or centuries between beats. Block faulting can create dramatic mountain landscapes. When a region of crust is being pulled apart, it can break into a series of blocks. Some blocks tilt and rise, forming mountain ranges. Others drop down, forming valleys or basins. The Basin and Range Province in the western United States is a classic example, with dozens of parallel mountain ranges separated by valleys, all created by normal faulting and crustal extension. The Wasatch Range in Utah is a particularly beautiful example. This range rises dramatically from the valley floor near Salt Lake City, lifted along the Wasatch Fault. The fault marks the boundary between the rising mountain block and the dropping valley block. The range front is steep and linear, following the fault trace. On the other side of the mountains, the slope is gentler, representing the tilted surface of the uplifted block. It's a textbook example of a fault block mountain range. Geologists can read these structures like text. By mapping folds and faults, by measuring the orientation of rock layers, by analyzing the types of deformation, they can reconstruct the forces that shaped a mountain range. They can determine whether rocks were compressed or extended, whether they were pushed from the east or the west, whether deformation happened quickly or slowly. The rocks remember their history, and with patience and skill, we can read that history. In some places, you can see these structures beautifully exposed. Road cuts through mountains often reveal folded layers, fault planes, or complex deformation. It's like looking at a cross-section through time, seeing not just the rock, but the process that shaped it. There's a particular pleasure in recognizing these features, in understanding that what looks like chaos is actually the result of orderly physical processes operating according to the laws of mechanics and thermodynamics. So when we look at mountains, we're not just seeing piles of rock. We're seeing the frozen record of forces, the evidence of stress and strain, compression and extension. We're seeing how rock responds when continents collide, when plates grind past each other, when Earth's crust is pulled and pushed and broken. And somehow, despite all this violence, albeit slow violence, the result is often beautiful. Sharp peaks, dramatic cliffs, sweeping valleys, the chaos of geological forces creating an orderly, if complex, landscape. Uplift and isostasy. Let's talk about a principle that's fundamental to understanding mountains, but which isn't immediately obvious. It's called isostasy, and it explains why mountains float, not on water, but on the denser rock of the mantle beneath them. This is where geology meets physics in a particularly elegant way, and understanding it helps explain not just how mountains rise, but how they persist and how they respond to changes in their mass. Imagine placing a wooden block in water. The block floats, but it doesn't float entirely on the surface. Part of it sits below the waterline, and the larger the block, the deeper it sits. This happens because the wood has to displace a volume of water equal to its weight. The wood is less dense than water, so it floats, but it has to push aside enough water to balance its weight. This is Archimedes' principle, named after the ancient Greek mathematician who supposedly discovered it while taking a bath. Now, Earth's crust behaves in a similar way. The crust is less dense than the mantle beneath it. Continental crust has a density of about 2.7 grams per cubic centimeter, while the mantle below has a density of about 3.3 grams per cubic centimeter. So it essentially floats on the mantle, which, remember, can flow slowly over geological time. Just like the wooden block, the crust doesn't sit entirely on top of the mantle. It extends down into it, and the thicker and higher the crust, the deeper it extends. This is the principle of isostasy, and it has profound implications for mountains. When tectonic forces push up a mountain range, they're not just piling rock on top of the surface, they're thickening the entire crust. If normal continental crust is about 35 kilometers thick, the crust beneath a major mountain range might be 60 or 70 kilometers thick. Just like that wooden block, the mountain has a root extending deep into the mantle, displacing the denser mantle rock and allowing the mountain to stand high. The Himalayas sit on crust that's about 70 kilometers thick, roughly twice as thick as normal continental crust. Beneath those soaring peaks, there's a massive root of buoyant continental crust extending deep into the mantle. This root is what supports the mountains, what allows them to stand so high. Without it, isostatic equilibrium would cause the mountains to sink until they reached a lower, more stable elevation. Here's where it gets interesting. As erosion wears down a mountain, removing rock from its surface, the mountain becomes lighter. According to isostasy, it should rise to compensate, bringing deeper rock closer to the surface. This is exactly what happens. Erosion and uplift work together in a kind of dance. As the mountain is eroded, it rises. Rock that was once deep in the crust is brought to the surface. The mountain wears down, but it also floats up, like a ship rising in the water as its cargo is unloaded. This means that the rocks you see at the surface of a mountain range aren't necessarily the rocks that were at the surface when the mountain first formed. They might be rocks that were once buried deep in the crust and have been exhumed by this combination of erosion and isostatic rebound. In some ancient mountain ranges, rocks that formed at depths of 20 or 30 kilometers, formed under pressures of several thousand atmospheres and temperatures of several hundred degrees Celsius, are now exposed at the surface, brought up by millions of years of erosion and uplift. Let's pause for a moment and think about what this means for the life of a mountain. Mountains don't simply rise and then sit static while erosion wears them down. The relationship between uplift and erosion is dynamic, a constant interplay. If erosion rate increases, uplift rate increases to compensate, at least until the crustal root has been largely removed. If tectonic forces stop pushing the mountain up, erosion will wear it down, but isostatic forces will continue to lift it for a while until the crust thins and equilibrium is reached at a lower elevation. The Appalachian Mountains provide a beautiful example of this principle. These mountains formed hundreds of millions of years ago and have long since stopped experiencing tectonic uplift, yet they still stand, still rise hundreds of meters above sea level. Why? Because as erosion removes material from the surface, isostatic forces cause the crust to rise, maintaining some elevation, even as the peaks are worn down. The Appalachians are being slowly recycled, with deep crustal rocks gradually being brought to the surface. Geologists can actually calculate how much rock has been removed from mountain ranges by measuring the difference between the elevation of the peaks and the thickness of the crustal root. In some cases, tens of kilometers of rock have been eroded away. The mountains we see today are just the stumps of what were once much higher peaks, and the rocks at the surface are rocks that were once buried deep in the crust. In the Alps, for example, geologists estimate that about 20 to 30 kilometers of rock have been removed by erosion since the mountains began forming. There's something quietly profound about this. Mountains are temporary. Even the Himalayas, currently Earth's highest peaks, will eventually be worn down. Erosion is patient and relentless. Water and ice, frost and chemical weathering slowly dismantle mountains grain by grain, carrying them away to the sea. But the process takes tens or hundreds of millions of years. From a human perspective, mountains seem eternal. From a geological perspective, they're transient features, rising and falling on a planetary surface that's constantly being renewed. Isostasy also explains why continents sit higher than ocean basins. Continental crust is thicker and less dense than oceanic crust, so it floats higher on the mantle. Oceanic crust is typically only about 7 kilometers thick and has a density of about 3.0 grams per cubic centimeter, denser than continental crust, but still less dense than the underlying mantle. Ocean basins are floored by this thin, dense oceanic crust that sits lower. The elevation difference isn't random. It's a direct consequence of the density and thickness of different types of crust. The average elevation of continents is about 840 meters above sea level, while the average depth of ocean basins is about 3,800 meters below sea level. This difference of about 4,600 meters is maintained by isostasy. If you could somehow magically remove all the water from the oceans, you'd see that Earth's surface has two distinct levels, the continental platforms and the ocean floors, separated by steep slopes called continental margins. When glaciers covered large parts of North America and Europe during ice ages, their enormous weight pushed down on the crust, depressing it. The ice sheets were up to 3 kilometers thick in places, representing an enormous load. Under this weight, the crust subsided, sinking into the mantle. When the glaciers melted, the crust slowly rebounded, rising back toward its original position. This process, called glacial isostatic adjustment, is still happening today. Parts of Scandinavia are rising by about a centimeter per year as the crust continues to recover from the weight of ice that melted more than 10,000 years ago. Hudson Bay in Canada is also rising, emerging from the sea as the land rebounds from its burden of ice. GPS measurements show that the uplift is fastest where the ice was thickest and decreases toward the edges of the former ice sheets. It's a reminder that the crust isn't rigid. It responds to changes in load, flexing and adjusting to maintain isostatic balance. This same principle affects mountains when they gain or lose ice. When glaciers grow on a mountain, their weight pushes the crust down slightly. When they melt, the crust rebounds. As climate warms and mountain glaciers around the world retreat, the mountains are very slowly rising in response, though the effect is small, measured in millimeters or less. Still, it's a reminder that mountains are not static. They're constantly adjusting to changes in their mass, responding to the addition or removal of material. Isostasy can create interesting effects in places where lots of sediment accumulates. River deltas, for example, can become so thick and heavy that they depress the crust beneath them. The Mississippi River Delta has subsided significantly under the weight of accumulated sediment. The sediment itself is buoyant, less dense than the mantle, but it's still heavy enough to push the crust down. As more sediment accumulates, the delta continues to subside, creating space for even more sediment. So as we rest here, comfortable and still, we can imagine the mountains doing the same thing. they're not just standing there, they're floating on the mantle, supported by their thick crustal roots. As erosion removes material from their peaks, they rise, slowly and steadily, maintaining some elevation despite the constant wearing down. It's a balance, a geological equilibrium, a system in constant adjustment. And it's been going on for as long as Earth has had mountains, for billions of years, a slow dance between gravity and buoyancy, between uplift and erosion. The role of erosion. Now let's turn our attention to the forces that tear mountains down, that work against the tectonic forces building them up. Erosion might seem like a simple process. Weather wears away rock, but it's actually a complex interaction of physical and chemical processes, all working together to dismantle mountains and carry their substance back to the sea. And paradoxically, erosion shapes mountains just as much as uplift does. The peaks and valleys we find so beautiful are largely the work of erosion, not just of tectonic forces. Water is the primary agent of erosion. Rain falls on mountains, gathering into streams that flow down slopes, carving channels and valleys. Rivers cut through rock, slowly deepening their channels, carrying away dissolved minerals and solid sediment. Even the gentlest stream, given enough time, can carve deep canyons through solid rock. The Grand Canyon is perhaps the most spectacular example, carved by the Colorado River over the past 5 to 6 million years, cutting down through layers of rock to create a chasm over a mile deep. But erosion begins even before water starts to flow. When water seeps into cracks in rock and freezes, it expands by about 9%, wedging the crack open wider. This frost wedging is particularly effective in mountains, where temperatures regularly cycle above and below freezing. Over many freeze-thaw cycles, solid rock can be broken into fragments, creating the scree slopes and talus fields often seen at the base of mountain cliffs. Imagine a crack in a rock face. Water seeps in during the day when temperatures are above freezing. At night, temperatures drop and the water freezes. The ice expands, pushing the walls of the crack apart. When the ice melts, the crack is slightly wider, allowing more water to enter. The cycle repeats night after night, year after year. Eventually, a piece of rock breaks free and tumbles down the mountainside, adding to the pile of debris below. Chemical weathering also plays a crucial role. Rainwater is slightly acidic, containing dissolved carbon dioxide from the atmosphere. This weak carbonic acid reacts with minerals in rock, particularly limestone and other carbonate rocks, slowly dissolving them. In tropical climates, where both temperature and rainfall are high, chemical weathering can be especially intense. In colder climates, physical weathering, the mechanical breaking of rock, tends to dominate. Limestone, made primarily of calcium carbonate, is particularly susceptible to chemical weathering. Rainwater dissolves the limestone, sometimes creating spectacular karst landscapes with sinkholes, caves, and underground rivers. In some limestone regions, the surface rock has been almost completely dissolved away, leaving only insoluble residues behind. The process is slow. It might take tens of thousands of years to dissolve even a few meters of limestone, but it's persistent and effective. Glaciers are particularly effective agents of erosion. When snow accumulates in high mountains faster than it melts, it compacts into ice, forming glaciers. These rivers of ice flow downhill under their own weight, moving slowly but inexorably. As they move, they pluck rocks from the bedrock and carry them along, using these rocks like sandpaper to grind away at the valley floor and walls. Glaciers can carve distinctive U-shaped valleys, quite different from the V-shaped valleys carved by rivers. The Matterhorn in the Swiss Alps is a classic example of glacial sculpting. This iconic pyramid-shaped peak was carved by glaciers approaching from multiple directions, each one cutting into the mountain and creating steep faces. Where the glaciers met, they left a sharp ridge, or arête. Where 3 or 4 glaciers carved into the same peak from different directions, they created a horn, a pyramidal peak with steep faces on all sides. The Matterhorn's distinctive shape is entirely the result of glacial erosion. Let's pause here and consider the timescales involved. Erosion is slow. A river might lower its channel by a millimeter per year in soft rock, much less in hard rock. Glaciers might carve a few centimeters deeper per year, though the rate varies dramatically depending on ice thickness, slope, and rock type. Chemical weathering dissolves rock even more slowly, at rates sometimes measured in tens or hundreds of meters per million years. Yet over geological time, these slow processes add up. Given a million years, barely a moment in Earth's history, erosion can lower a landscape by hundreds of meters. The rate of erosion varies dramatically depending on climate, rock type, and relief. In high, steep mountains with abundant precipitation, erosion can be very fast, several millimeters per year. In gentle, arid landscapes, erosion might be 100 times slower. This is why mountains in wet, tropical regions tend to be more deeply dissected and rugged than mountains in dry regions. The Andes in Peru, for example, which receive heavy rainfall, have steep, deeply carved valleys. Mountains in the Atacama Desert, one of the driest places on Earth, are gentler and less dissected. There's a fascinating feedback between uplift and erosion. As mountains rise, they create steeper slopes. Steeper slopes mean faster erosion. Rivers cut deeper, landslides become more common, glaciers carve more effectively. In some mountain ranges, erosion is so rapid that it nearly keeps pace with uplift. The mountains grow, but they don't get much higher because erosion removes material as quickly as tectonic forces add it. This creates a kind of steady state where the mountain maintains a certain elevation, even though both uplift and erosion are actively occurring. Some geologists believe that erosion can actually influence tectonics. When erosion removes rock from the surface, it reduces the load on the crust. This can cause isostatic uplift, as we discussed earlier, but it might also affect the distribution of stress in the crust, potentially influencing where and how deformation occurs. In this view, erosion isn't just a passive consequence of mountain building, it's an active participant in shaping mountain ranges. Rivers don't just erode vertically, cutting down into rock. They also erode laterally, widening their valleys. As a river meanders, and all rivers naturally develop curves, the water flows faster on the outside of bends, eroding the bank there, while it flows slower on the inside of bends, depositing sediment. Over time, this creates a sinuous path, with the river slowly migrating back and forth across its valley. In mountains, this lateral migration can be limited by the steep valley walls, but it still occurs, especially in wider valleys where the river has more room to wander. Landslides and mass wasting are also important erosional processes in mountains. On steep slopes, gravity is constantly trying to pull rock and soil downward. Sometimes this happens slowly, through gradual creep. Other times, it happens catastrophically, when a cliff face collapses or a mountainside slumps. These mass movements can reshape mountain landscapes dramatically, sometimes in just seconds or minutes, undoing the work of thousands of years of gradual uplift. The 1980 eruption of Mount St. Helens included a massive landslide, the largest recorded in history. The north face of the mountain collapsed, sending about 2.3 cubic kilometers of rock and ice sliding down the mountain at speeds up to 240 kilometers per hour. The landslide removed about 400 meters from the mountain's height and completely reshaped its profile. It was a stark reminder that mountains can change rapidly, that erosion isn't always gradual. The debris carried away by erosion doesn't disappear. It's transported downstream, eventually reaching the ocean where it settles out, forming new sedimentary layers on the ocean floor. These sediments might eventually be buried, compressed into rock, and then uplifted to form new mountains in the next cycle of plate tectonics. In this way, mountains are recycled. The Himalayas of today contain rock that was once part of ancient, long-vanished mountain ranges. The sediment washing off the Himalayas today might, in 100 million years, be part of new mountains somewhere else on Earth. In fact, the sand on beaches, the silt in river deltas, the mud on the ocean floor, all of it came from mountains. Every grain of sand was once part of a mountain somewhere. When you walk on a beach, you're walking on the ruins of ancient peaks, rock that has been broken down and transported and finally deposited where waves lap at the shore. There's something poetic about that. Mountains don't truly die. They transform, becoming the raw material for new landscapes, new rocks, eventually new mountains. So erosion isn't the enemy of mountains. It's their sculptor, their shaper, their companion in the slow dance between uplift and wearing down. Without erosion, mountains would be smooth, featureless bulges on Earth's surface. With erosion, they become spectacular landscapes of peaks and valleys, cliffs and canyons, ridges and gorges. Erosion gives mountains their character, their beauty, their complexity, and it ensures that mountains are never static, never finished, always changing, always being reshaped by wind and water, ice and gravity. Different mountain types. Let's take a gentle journey through the different types of mountains that exist on Earth. We've touched on some of these already, but now we can explore them more systematically, understanding not just how they form, but how to recognize them. What makes each type unique? Mountains are not all alike, and understanding their differences helps us read the landscape, to see not just what is, but how it came to be. Fold mountains are perhaps the most common type, formed when layers of rock are compressed and bent into folds. These are the mountains we've discussed most, formed at convergent plate boundaries where continents collide. The Himalayas, the Alps, the Appalachians, the Rockies, all are fold mountains, though they're at different stages of their life cycle. Young fold mountains like the Himalayas are high and rugged. Old fold mountains like the Appalachians are lower and more rounded, worn down by hundreds of millions of years of erosion. When you look at fold mountains, you're often seeing layers of sedimentary rock, limestone, sandstone, shale, that were deposited flat and horizontal on ancient seafloors or in river deltas, then compressed and folded when continents collided. These layers are sometimes tilted nearly vertical, sometimes folded into complex patterns. Road cuts through fold mountains often reveal these spectacular folds, layer after layer of rock bent into curves, a frozen record of continental collision. Fault block mountains form when the crust breaks along faults, and blocks of rock are tilted or lifted. The Basin and Range Province in the western United States is the classic example, with alternating mountain ranges and valleys created by normal faulting as the region is stretched. The Wasatch Range in Utah, the Sierra Nevada in California, the Teton Range in Wyoming, all are fault block mountains. These mountains often have a distinctive asymmetric profile. One side, the fault scarp, is steep and linear, marking where the block was lifted along the fault. The other side slopes more gently, representing the tilted surface of the uplifted block. If you see a mountain with one very steep side and one gentler side, there's a good chance you're looking at a fault block mountain. Volcanic mountains we've already discussed extensively. These include stratovolcanoes like Mount Fuji and Mount Rainier, shield volcanoes like Mauna Loa, and cinder cones, small steep-sided hills built from ejected volcanic material. Each type has its own characteristic shape, reflecting the type of magma and style of eruption that built it. Stratovolcanoes are built from alternating layers of lava flows and ash deposits, creating steep composite cones. They're often symmetrical, with a crater at the summit where eruptions occur. Shield volcanoes are broad and gently sloping, built from fluid basaltic lava that flows easily. Cinder cones are small and steep, built from fragments of lava ejected into the air during fountaining eruptions, falling back around the vent and building a cone of loose material. Dome mountains form when magma pushes up from below but doesn't break through to the surface. Instead, it lifts the overlying rock layers, creating a dome-shaped bulge. The Black Hills of South Dakota are an example, where an upwelling of magma about 60 million years ago lifted the overlying sedimentary layers into a dome. Erosion has since removed the upper layers, exposing the granite core of the uplift and creating the current landscape. Let's pause for a moment and think about how these different mountain types might exist side by side. In some regions, you can find multiple types of mountains in close proximity, each telling a different part of the region's geological story. In the western United States, for example, you have fold mountains, the Rockies, fault block mountains, the Basin and Range, volcanic mountains, the Cascades, and even dome mountains, the Black Hills. Each range formed at a different time, by different processes, but they're all part of the same larger story of North American tectonics. Plateau mountains, or erosional mountains, form when a relatively flat plateau is uplifted and then carved by erosion into a landscape of peaks and valleys. The Colorado Plateau in the southwestern United States is an example. The plateau itself was lifted by tectonic forces, but the spectacular scenery, the Grand Canyon, Zion, Bryce Canyon, was carved by erosion. These aren't mountains in the traditional sense, but they're elevated terrain with dramatic topography. The Catskill Mountains in New York are another example of erosional mountains. Despite being called mountains, they're actually a dissected plateau, a flat-lying plateau, that's been carved by streams into a landscape that looks mountainous. The rock layers are still nearly horizontal, unlike in fold mountains where the layers are tilted and folded. But erosion has created deep valleys between the remaining high ground, giving the appearance of mountains. In some cases, mountains can be combinations of types. The Rockies, for example, are primarily fold mountains, formed by compression related to plate tectonics. But they also include some volcanic features, some fault block structures, and areas where ancient domes have been exposed by erosion. Real mountains are complex, often incorporating multiple formation processes over their long history. Understanding mountain types helps us understand plate tectonics and Earth's geological history. Volcanic mountains mark subduction zones, or hotspots. Fold mountains mark collision zones. Fault block mountains indicate regions where the crust is being stretched. By mapping different mountain types, geologists can reconstruct the tectonic history of a region, determining where plates have collided, where they've separated, where volcanoes have been active. There's also a category we might call submarine mountains, mountains that exist beneath the ocean. Mid-ocean ridges are the longest mountain ranges on Earth, stretching for about 65,000 kilometers around the globe, like the seam on a baseball. These underwater mountains mark divergent plate boundaries, where new oceanic crust is being formed. Though we can't see them without special equipment, they're just as much mountains as the Himalayas or Rockies. Seamounts are isolated underwater mountains, often extinct volcanoes. There are estimated to be more than 100,000 seamounts in the world's oceans, most of them formed by hotspot volcanism. Some seamounts rise close enough to the surface to affect shipping. Others are thousands of meters below the surface, unknown except to researchers using sonar to map the ocean floor. Their mountains we'll never climb, peaks we'll never see, but they're part of the same system that builds mountains on land. Geos are flat-topped seamounts, underwater mountains that were once volcanic islands. They formed above sea level, and wave action eroded their tops flat. Then, as the tectonic plate carried them away from the hotspot, they subsided, sinking below sea level and leaving flat-topped underwater mountains. They're fossil islands, remnants of lands that once existed but now lie beneath the waves. So when we talk about mountains, we're talking about a diverse family of landforms, each with its own origin story, its own characteristics, its own role in Earth's geological processes. Some are young and actively growing. Others are ancient and being worn away. Some are volcanic and might erupt. Others are stable blocks of uplifted crust. Each type tells us something about the forces that shaped it, about the tectonic setting in which it formed, about the history of the region, and all of them, in their different ways, reach toward the sky, adding vertical dimension to our planet's surface, creating the varied and beautiful landscapes we treasure. Time and patience. Now let's step back and think about time, about the vast expanses of geological time over which mountains form and erode. This is perhaps the most challenging aspect of understanding mountains. truly grasping the timescales involved. We live such short lives, experiencing perhaps 100 years at most. Mountains, by contrast, measure their lives in millions or tens of millions of years. The disconnect between human timescales and geological timescales is profound, and bridging that gap requires a different way of thinking about time. The Himalayas began forming about 50 million years ago when India collided with Eurasia. 50 million years. Let's pause and really consider what that means. Modern humans, Homo sapiens, have existed for only about 300,000 years. All of recorded human history spans about 5,000 years. The Himalayas have been rising for 10,000 times longer than human civilization has existed. For 160,000 times longer than you've been alive if you're 30 years old. If you could somehow watch the Himalayas forming and fast forward, with each year compressed into a second, the entire 50 million year history of the range would take about 19 months to watch. You'd see the mountains rise, slowly but steadily, like plants growing in time-lapse photography. You'd see them weather storms, accumulate and lose glaciers, be eroded and uplifted. But in real time, the process is imperceptibly slow. You could spend your entire life in the Himalayas and never see the mountains noticeably grow. The Appalachian Mountains are even older. They formed about 480 to 300 million years ago during a series of mountain-building events as continents collided to form the supercontinent Pangaea. At their peak, they may have been as high as the Himalayas are today. But they've been eroding for hundreds of millions of years, worn down by water and ice, wind and gravity. The mountains we see today are just the deeply eroded stumps of what were once towering peaks. Think about that for a moment. These mountains have stood for longer than dinosaurs existed. Dinosaurs appeared about 230 million years ago and went extinct 66 million years ago. The Appalachians were already ancient when the first dinosaurs walked the earth. They watched as life moved from sea onto land. They were ancient when the first forests grew. They were old when the first coal swamps formed in their shadow. And they're still here, still standing, though much reduced from their former glory. There's something almost comforting about that persistence, that endurance across unimaginable spans of time. Geologists divide Earth's history into eons, eras, periods, and epochs, a nested hierarchy of time units. The current eon, the Phanerozoic, began about 541 million years ago and continues to the present. Within that eon, we've had multiple periods of major mountain building, called orogenies. Each orogeny is associated with the collision of continents, the closing of ocean basins, the formation of supercontinents, and each has left its mark in mountain ranges, some still prominent, others eroded nearly flat. The oldest rocks on Earth are about 4.4 billion years old, nearly as old as the planet itself. Earth formed about 4.54 billion years ago. That's a number difficult to comprehend, 4.5 billion years. If you tried to count to 4.54 billion, counting one number per second without stopping, it would take you more than 140 years. And that's how many years old our planet is. Slowly, gently, let's think about what this means for mountains. The mountains we see today are just the latest generation in a long succession of mountain ranges that have risen and been eroded away. Before the Himalayas, there were other mountains in other places. Before the Appalachians, there were mountains whose names we've forgotten, whose very rocks have been so thoroughly recycled that we can barely trace their existence. Mountains come and go, but the process of mountain building continues as long as Earth's interior remains hot, as long as convection currents churn the mantle, as long as tectonic plates move across the surface. Scientists have identified several major periods of mountain building in Earth's history. The Grenville orogeny, about 1 billion years ago, built mountains whose remnants can be found in eastern North America and Scotland. The Caledonian orogeny, about 400–500 million years ago, formed mountains in Scotland and Scandinavia. The Alleghenian orogeny, about 320–260 million years ago, built the Appalachians. The Alpine orogeny, still ongoing, is building the Alps, the Carpathians, and other European mountains. Each orogeny is a chapter in Earth's geological story. And here's something wonderful to consider. The mountain building happening right now, the rise of the Himalayas, the continued growth of the Andes, the volcanism in the Cascades, is not unique or special. It's just business as usual for planet Earth. Mountains have been forming and eroding for billions of years, and they'll continue to form and erode for billions more, at least until Earth's interior cools enough that plate tectonics stops. And that won't happen for a very, very long time. Let's pause here and breathe slowly. The pace of geological change is, in its way, deeply calming. There's no urgency in mountain building. Mountains don't rush. They simply rise, millimeter by millimeter, following the inexorable physics of plate tectonics. Even the most dramatic geological events, massive earthquakes, volcanic eruptions, are just small steps in long processes. A large earthquake might uplift a mountain by several meters. That seems dramatic. But in the context of millions of years of mountain building, it's barely a heartbeat. Geologists use various methods to determine the age of rocks and the timing of geological events. Radiometric dating, which measures the decay of radioactive elements in rocks, can tell us how old a rock is, when a volcanic eruption occurred, or when metamorphism happened. Different radioactive elements decay at different rates, providing clocks that work on different timescales. Carbon-14 is useful for dating things up to about 50,000 years old. Uranium-238, which decays much more slowly, can be used to date rocks billions of years old. By dating rocks from different levels in a mountain range, geologists can reconstruct the history of uplift and erosion, determining when the mountains began to rise and how quickly they've been growing. They can determine when volcanic eruptions occurred, when metamorphic events happened, when rocks that were once deep in the crust were brought to the surface. In the Himalayas, geologists have found that uplift accelerated about 25 million years ago, possibly because erosion had worn away enough of the mountains that isostatic forces caused rapid uplift of deeper rocks. They found that some peaks are rising faster than others, that the pattern of uplift is complex and varies across the range. They've traced the movement of India northward, calculating exactly how fast it's been moving and when it collided with Eurasia. All of this detective work relies on careful measurement, sophisticated instruments, and complex calculations. But you don't need sophisticated instruments to appreciate geological time. You can see it in rock layers exposed in road cuts, each layer representing a period of deposition, sometimes spanning thousands or millions of years. You can see it in the roundness of ancient mountains versus the sharpness of young ones. You can see it in fossils, in the type of rocks present, in the degree of metamorphism. The landscape itself is a record of time if you know how to read it. There's something almost meditative about thinking on geological timescales. It puts human concerns in perspective. Our lives are brief flickers. Even human civilization, all our cities and monuments, will eventually be dust. But the mountains endure. Not forever. Nothing lasts forever. But for timescales so vast they approach the infinite from our perspective. And somehow that's comforting. The mountains were here before us. They'll be here after us. The slow, patient processes that built them continue regardless of human activity. Looking forward, we can predict with some confidence what will happen to mountains over the next millions of years. Current mountain ranges will continue to rise where tectonic forces are active. The Himalayas will keep growing as India pushes into Eurasia. The Andes will continue to build as the Nazca Plate subducts beneath South America. And all mountains will continue to erode, grain by grain, carried away by water and wind. But on longer timescales, hundreds of millions of years, the configuration of continents will change. Plates that are now colliding might start to diverge. New subduction zones might form. The Atlantic Ocean might close, bringing the Americas back together with Europe and Africa. Or the Pacific Ocean might close, bringing the Americas into collision with Asia. Either way, new mountain ranges will form, perhaps exceeding even the Himalayas in height. And current mountain ranges will be worn away, their rocks recycled into new landscapes. The mountains teach us patience. They remind us that even the mightiest changes happen slowly. They show us that persistence, not speed, is what shapes the world. And they invite us to think on timescales beyond our normal experience, to see our planet not as a static backdrop, but as a dynamic system, constantly in motion, constantly being renewed. The mountains are patient teachers, and their lessons are worth pondering as we drift towards sleep. Mountain ecosystems. Mountains aren't just geological features, they're ecosystems, habitats, homes for countless species of plants and animals. The same forces that create mountains also create ecological opportunities, niches for life to fill. And life, being remarkably adaptable, has filled those niches in extraordinary ways. Let's explore how mountains create unique environments and how life has adapted to survive in these challenging places. As you climb a mountain, you pass through different climate zones. At the base, conditions might be warm and temperate, perhaps even tropical if the mountain is near the equator. As you ascend, temperature decreases. For every 1,000 meters of elevation you gain, temperature drops by about 6.5 degrees Celsius. This means that climbing a high mountain is, in some ways, like traveling from the equator toward the poles. You pass through different ecological zones, each with its own characteristic plants and animals, just by going up. In tropical regions, mountains might start in rainforest at their base. As you climb, you pass through cloud forest, perpetually misty, draped with moss and epiphytes, a world of constant moisture where condensation drips from every leaf. Higher still, you enter elfin forest, where trees are stunted by cold and wind, their gnarled branches twisted by constant exposure to harsh conditions. Above the tree line, only hardy grasses, shrubs, and alpine wildflowers survive. And at the highest elevations, you find only bare rock and ice, where almost nothing can live. Each zone is distinct, separated by altitude rather than latitude. The tree line, the elevation above which trees cannot grow, is one of the most dramatic boundaries in mountain ecosystems. Below it, forests. Above it, alpine meadows or tundra. The exact elevation of the tree line varies with latitude. Near the equator, tree line might be at 4,000 meters or higher. In the Arctic, tree line is at sea level or only slightly above. But wherever it occurs, it marks a fundamental change in the environment, a boundary beyond which trees cannot survive the harsh conditions. What limits tree growth at high elevations? It's a combination of factors. Low temperatures slow metabolism and make it difficult for trees to photosynthesize efficiently. Short growing seasons mean trees have only a few months each year to grow. Strong winds can damage tissues and increase water loss through transpiration. Frost can occur at any time of year, potentially damaging new growth. Soils are often thin and poor in nutrients. All these factors combine to make it impossible for trees to survive above a certain elevation. Alpine plants have evolved fascinating adaptations to survive in this harsh environment. Many grow close to the ground in cushion or mat forms, avoiding the worst of the wind. Some have dense, hairy coverings that insulate them and reduce water loss. Many complete their entire life cycle in the brief summer growing season, flowering and setting seed quickly before winter returns. Alpine wildflowers are often brilliantly colored, attracting the few pollinators that venture to these heights. Let's pause for a moment and think about an alpine flower, perhaps a gentian or a saxifrage, growing in a rocky crevice near the summit of a mountain. This plant might be decades or even centuries old, growing only a few millimeters each year. It experiences extreme temperature swings, baking sun during the day, freezing cold at night. It endures months buried under snow. Yet, it survives, and in summer, it produces flowers of stunning beauty, as if to prove that life can flourish even in the harshest conditions. Animals, too, have adapted to mountain environments. Some, like mountain goats and bighorn sheep, are superbly suited to steep, rocky terrain with specialized hooves that grip on bare rock. Their bodies are stocky and powerful, with low centers of gravity that make them stable on precarious perches. They can leap across gaps that would terrify a human, landing securely on tiny ledges. Others, like pikas, small relatives of rabbits, live in talus fields, piles of broken rock at the base of cliffs. Pikas are remarkably industrious, spending their summer cutting grass and wildflowers, drying this hay in the sun, and then storing it in their burrows to eat during the long winter. They don't hibernate. Instead, they survive the winter under the snow, eating their stored food and venturing out only rarely. Mountain birds often have shorter wings than their lowland relatives, an adaptation to the strong, gusty winds common at high elevations. Shorter wings provide better maneuverability in turbulent air. Some birds, like the Himalayan snowcock, live year-round at elevations above 4,000 meters, adapted to life in perpetual cold and thin air. Let's think gently about what it means to live on a mountain. The air is thinner, containing less oxygen. At 5,000 meters elevation, the air pressure is only about half what it is at sea level, meaning each breath contains only half as much oxygen. This makes physical exertion difficult and requires adaptations to survive. Many high-altitude animals have larger lungs, more red blood cells, or hemoglobin that binds oxygen more efficiently. Temperatures are colder. The growing season is shorter. Winds are stronger. UV radiation is more intense at high elevations, where there's less atmosphere to filter it. Water might be scarce during parts of the year, frozen during others. Yet despite all these challenges, life persists. Evolution has found ways to survive in these harsh environments, and mountain ecosystems, though less diverse than lowland ecosystems, are no less remarkable. Mountains also create barriers that isolate populations. A species living on one mountain range might be separated from populations on another range by valleys or lowlands that act as barriers to movement. This isolation can lead to speciation, the evolution of new species. Many mountains harbor endemic species, found nowhere else on Earth. The unique environmental conditions and geographic isolation of mountains make them hotspots of biodiversity and evolution. The Hawaiian Islands provide a beautiful example. Each island is a volcanic mountain rising from the ocean floor. When new species colonize an island, they find a variety of habitats at different elevations. Populations become isolated in different habitat zones or on different islands, and over time they diverge, evolving into new species. The Hawaiian honeycreepers, for example, evolved from a single ancestral species into dozens of distinct species, each adapted to different foods and habitats. Mountains create evolutionary opportunity. Mountains also influence climate patterns over much larger areas. When moisture-laden air encounters a mountain range, it's forced to rise. As it rises, it cools, and water vapor condenses, forming clouds and precipitation. The windward side of the mountain, the side facing the wind, receives abundant rainfall. But once the air crosses the mountain and descends on the other side, it warms and dries. The leeward side of the mountain lies in a rain shadow, receiving much less precipitation. The Cascade Range in the Pacific Northwest demonstrates this beautifully. The western slopes, facing the Pacific Ocean, receive enormous amounts of rain and snow. Some areas receive over 5,000 millimeters per year, creating temperate rainforests with towering trees draped in moss. But east of the Cascades, the climate is much drier, receiving less than 300 millimeters per year in some areas, almost desert-like. The same pattern occurs with the Sierra Nevada in California, the Andes in South America, and mountain ranges worldwide. Mountains create their own climate patterns, profoundly influencing ecosystems on both their slopes and in adjacent regions. Glaciers that form on high mountains are important water sources for lowland areas. They accumulate snow during winter and release meltwater during summer, when water is often most needed. Many of the world's major rivers, including the Ganges, the Indus, the Yangtze, and rivers in the western United States, depend on mountain snowpack and glaciers for a significant portion of their flow. Without mountains, these rivers would be much smaller, and the civilizations that depend on them might never have developed. The Ganges River, for example, is fed by glaciers in the Himalayas. During the dry season, when monsoon rains have ceased, meltwater from these glaciers keeps the river flowing. This water irrigates crops, provides drinking water, and supports ecosystems all the way to the Bay of Bengal. The people of the Ganges Plain have depended on these mountain waters for thousands of years, but mountains are changing. Global climate change is affecting mountain ecosystems in profound ways. Glaciers are retreating, snowpack is decreasing, tree lines are moving upward as temperatures warm. Species adapted to cool conditions are being squeezed into smaller and smaller areas at higher elevations. Eventually, there may be nowhere left for them to go. Some mountain species face extinction as their habitats literally disappear beneath them. There's something poignant about this. Mountains, which seem so permanent, so unchanging, are actually sensitive to climate. The ice and snow that cap high peaks are fragile, dependent on a delicate balance of temperature and precipitation. Small changes in climate can have large effects, and while mountains have certainly experienced climate changes in the past, advancing glaciers during ice ages, retreating glaciers during warm periods, the current rate of change is unusually rapid, potentially too rapid for some species to adapt. Yet mountains remain refuges. During ice ages, when lowlands were covered by glaciers, some mountain peaks remained ice-free, providing refuges for plants and animals. During warm periods, mountain slopes provide cooler habitats for species adapted to cold. Mountains are refuges across time, harboring species through climate changes, allowing life to persist even as conditions shift. They're reservoirs of biodiversity, seed banks of genetic diversity. So when we look at mountains, we shouldn't see just rock and ice. We should see ecosystems, habitats, homes for countless species. We should see evolutionary laboratories, places where isolation and unique environmental conditions drive the evolution of new forms. We should see climate regulators, water towers, refuges. Mountains are not just geological features, they're living landscapes, integral parts of Earth's biosphere, as important to life as they are impressive to behold. Mountains in human culture. Mountains have captivated human imagination throughout history. They've been seen as sacred, as dangerous, as challenges to overcome. They've inspired myths and legends, religions and philosophies. They've marked boundaries between nations and cultures, and they continue to draw people seeking adventure, solitude, spiritual experiences, or simply stunning views. Let's explore the relationship between humans and mountains, a relationship that's as old as our species. Many cultures have considered mountains to be the homes of gods. The ancient Greeks believed their gods lived on Mount Olympus, the highest peak in Greece. Hindus and Buddhists consider Mount Kailash in Tibet to be sacred, the center of the universe, the abode of the god Shiva. Mount Fuji is sacred in Japanese Shinto tradition. Mountains, reaching toward the sky, have been seen as links between earth and heaven, between the human and divine realms. Perhaps it's because mountains seem to touch the clouds, to exist partially in another realm, that they've been associated with the sacred. In many indigenous cultures, specific mountains are considered sentinels, protectors, or ancestors. The Maori of New Zealand have deep spiritual connections to mountains in their territories. Many Native American tribes have sacred mountains. The Navajo, for example, recognize 4 sacred mountains that bound their traditional homeland. These aren't just geographical features, they're integral to cultural identity and spiritual practice. Mountains have also been feared. They're places of harsh weather, difficult terrain, rockfalls, and avalanches. Early explorers often considered them obstacles to be avoided rather than challenges to be climbed. The idea of climbing a mountain for sport or pleasure is relatively recent in human history. For most of human civilization, mountains were barriers to cross or obstacles to avoid, not destinations in themselves. But mountains have always been important boundaries. Mountain ranges often mark the borders between countries or cultures. The Pyrenees separate Spain and France. The Alps divide northern and southern Europe. The Himalayas separate the Indian subcontinent from the rest of Asia. These are not arbitrary boundaries drawn on maps. They're natural boundaries created by geography. Mountains are difficult to cross, especially with large groups or armies, so they've historically separated human populations, allowing different cultures to develop on either side. This isolation has affected human history in profound ways. Languages, customs, technologies, and political systems develop differently on opposite sides of mountain ranges. The difficulty of crossing mountains limited trade and communication. Passes through mountain ranges, like the Khyber Pass connecting Central Asia and the Indian subcontinent, or the Brenner Pass through the Alps, became strategically important, fought over and controlled because they were the few places where large-scale movement across the mountains was possible. Yet people have always lived in mountains. Highland peoples have developed unique cultures adapted to mountain environments. They've learned to farm on steep slopes using terracing, creating level platforms where crops can grow. The rice terraces of the Philippines, the agricultural terraces of the Andes. These are marvels of engineering, allowing agriculture in places where it would otherwise be impossible. They've learned to breed animals, yaks, llamas, alpacas, suited to high altitudes. Yaks thrive at elevations where cattle would struggle, providing meat, milk, wool, and transportation for Tibetan and Himalayan peoples. Llamas and alpacas serve similar roles in the Andes, adapted to thin air and cold temperatures. They've learned to build houses that withstand harsh weather and to navigate difficult terrain. Mountain peoples often have distinct identities, shaped by the challenging environments they inhabit. The Sherpa people of the Himalayas, the Quechua of the Andes, the various ethnic groups of the Caucasus, all have developed unique cultures in their mountain homes. The conquest of mountains is a relatively recent phenomenon. Mount Blanc in the Alps was first climbed in 1786 by Jacques Balmat and Michel Paccard, marking perhaps the beginning of mountaineering as we know it. The Matterhorn was first summited in 1865, though the triumph was marred by tragedy when 4 of the 7 climbers died during the descent. Mount Everest wasn't climbed until 1953, when Edmund Hillary and Tenzing Norgay reached the summit. These climbs captured public imagination and helped establish mountaineering as a sport and an adventure pursuit. But there's something troubling about the language of conquest. Mountains don't exist to be conquered. They're not enemies to be defeated. Perhaps it's better to think of mountain climbing as a dialogue with the mountain, an attempt to understand and work with the terrain rather than to dominate it. Many modern mountaineers speak of the mountains in terms of respect rather than conquest, acknowledging the mountain's power and their own vulnerability. Let's pause here and think about what draws people to mountains. Part of it is certainly the challenge, the physical and mental demands of climbing. Part is the beauty, the spectacular views and dramatic landscapes. But perhaps part of it is also a desire to encounter something larger than ourselves, something that puts human scale in perspective. Standing on a mountain peak, looking out over vast distances, you feel both small and connected, insignificant in size but part of something vast. Mountains have inspired art and literature throughout history. The Romantic poets of the 18th and 19th centuries wrote extensively about mountains, celebrating their sublimity, the mixture of beauty and terror they evoked. Artists like Caspar David Friedrich and Albert Bierstadt painted mountains, trying to capture their scale and majesty. Photographers have made entire careers photographing mountain landscapes. There's something about mountains that demands to be represented, to be shared, to be contemplated. Mountains are also economically important. They're sources of minerals. Many valuable ore deposits form in mountain belts where hot fluids circulate through fractured rock, depositing metals. They're sources of water for agriculture and hydroelectric power. They attract tourism, with millions of people visiting mountain regions each year for recreation, skiing, hiking, and sightseeing. The economies of entire regions depend on mountains. But this economic importance comes with challenges. Tourism can damage fragile mountain ecosystems. Trails become eroded. Popular peaks become crowded. Waste accumulates. Finding ways to allow people to experience mountains while minimizing environmental impact is an ongoing challenge, requiring careful management and respect for these complex environments. Some mountains have become symbols. Mount Fuji represents Japan in countless artworks and photographs. The Matterhorn has become a symbol of Switzerland, even appearing in the logo of a famous chocolate brand. Half Dome represents Yosemite, and by extension, the American conservation movement. These individual mountains stand for something larger than themselves, becoming cultural icons, instantly recognizable symbols of places or ideas. The Himalayas, perhaps more than any other mountain range, have captured global imagination. The highest peaks on Earth, they've drawn mountaineers from around the world. The deaths that have occurred there, about 300 on Mount Everest alone, add to their mystique. Yet the Himalayas are also home to millions of people, not just destinations for adventure tourism. They're living, working landscapes, not just beautiful backdrops for extreme sports. Mountains continue to inspire spiritual experiences. Many people report feeling something profound when in mountains, a sense of peace, of connection, of perspective. Maybe it's the grandeur of the landscape. Maybe it's the physical exertion required to reach high places. Maybe it's the thin air affecting brain chemistry. Or maybe there's something inherently meaningful about mountains, about these places where Earth reaches upward, where rock meets sky, where the usual rules of lowland life don't apply. So mountains are not just geological features. They're cultural touchstones, spiritual destinations, economic resources, recreational playgrounds, scientific laboratories. They're woven into human culture and history as thoroughly as they're woven into Earth's geology. And as we lie here, relaxed and comfortable, we can think of all the people throughout history who have looked at mountains with wonder, fear, reverence, or determination. Mountains have witnessed all of human history, silent observers of our brief civilizations, standing as reminders that some things transcend human concerns. The future of mountains. Now let's look forward, toward the future of mountains. What will happen to the mountain ranges we see today? What new mountains might form? How will climate change and human activity affect these landscapes? The future is, by definition, uncertain, but we can make some educated guesses based on what we know about Earth's processes and current trends. The most obvious prediction is that current mountain building will continue. The Indian plate is still pushing into Eurasia at about 50 millimeters per year, so the Himalayas will keep rising. The collision won't stop tomorrow or next year, or even in the next million years. It will continue for tens of millions of years, at least until plate motions change, or until so much continental crust has been piled up that the forces driving convergence can no longer overcome the buoyancy and strength of the thickened crust. The Himalayas, already the highest mountains on Earth, might grow even higher, though erosion will constantly work to wear them down. The competition between uplift and erosion will continue, with the height of the mountains representing a balance between these two opposing forces. In some areas, uplift is winning, and the mountains are getting higher. In others, erosion is keeping pace with or exceeding uplift, and the mountains are being lowered. Similarly, the Andes will continue to grow as the Nazca Plate continues to subduct beneath South America at about 70 millimeters per year. The volcanoes of the Pacific Ring of Fire will continue to erupt, building their peaks higher. The East African Rift will continue to widen, eventually splitting the continent. These processes, set in motion millions of years ago, have tremendous momentum. They won't stop on human timescales or even on timescales of thousands or millions of years. But on longer timescales, tens or hundreds of millions of years, plate motions will change. Plates that are currently converging might start to diverge. Plates that are diverging might stop spreading. New subduction zones might form, old ones might cease. the configuration of continents will change. In a few 100 million years, Earth's geography might be unrecognizable, with continents in different positions, new mountain ranges forming, and old ones eroded away. Some geologists predict that the continents will eventually come together again, forming a new supercontinent. This has happened before. About 300 million years ago, most of Earth's continental crust was assembled into a supercontinent called Pangaea. Before that, there were other supercontinents: Rodinia about 1 billion years ago, Nuna about 1.8 billion years ago. The cycle of supercontinent formation and breakup, called the Wilson cycle after the geophysicist J. Tuzo Wilson who first proposed it, seems to repeat roughly every 500 to 700 million years. If current trends continue, some geologists predict that a new supercontinent might form about 250 million years from now. They've even given it speculative names: Pangaea Ultima, Nova Pangaea, Amasia. Though of course, these are just predictions based on extrapolating current plate motions. Where might this supercontinent form? Perhaps the Atlantic Ocean will close, bringing the Americas back together with Europe and Africa. Or perhaps the Americas will collide with Asia as the Pacific Ocean closes. Either way, new mountain ranges would form where continents collide, mountain ranges that might rival or exceed the Himalayas in height. But let's bring our timeline back to something more immediately relevant. What will happen to mountains over the next few centuries or millennia? Climate change is already affecting mountain environments in ways both subtle and dramatic. Glaciers are retreating worldwide. Some small glaciers have disappeared entirely. Larger glaciers are shrinking, some dramatically so. This loss of ice has several consequences beyond the obvious aesthetic change. It affects mountain ecosystems. Species that depend on permanent snowfields or glaciers are losing their habitat. It reduces water storage. Mountain glaciers act as natural reservoirs, accumulating snow in winter and releasing meltwater in summer. As glaciers shrink, this buffering effect is reduced. Rivers that depend on glacial meltwater may have reduced flows during dry seasons, affecting agriculture, drinking water supplies, and hydroelectric power generation. It changes the appearance and character of mountain landscapes. Mountains that have been permanently snow-capped for thousands of years are losing their snow. The bare rock beneath is being exposed for perhaps the first time in millennia. This changes not just how the mountains look, but how they function ecologically and hydrologically. Permafrost, permanently frozen ground, is thawing in many mountain regions. This can destabilize slopes, increasing the frequency of landslides and rockfalls. Infrastructure in mountain regions, buildings, roads, ski resorts, is at risk from thawing permafrost. The ice that has held rock and soil in place is melting, and slopes that have been stable for thousands of years are beginning to move. Tree lines are moving upward as temperatures warm. Species adapted to cool conditions are being pushed to higher elevations. Some species will go extinct, unable to adapt fast enough, or unable to move to suitable habitat because they're already at the tops of mountains. Mountain ecosystems will change, possibly dramatically. The mountains as physical features will persist, but the communities of plants and animals living on them will be different, possibly impoverished. Human activities are also affecting mountains more directly. Tourism brings both benefits and challenges. It provides economic opportunities for mountain communities, but can also damage fragile ecosystems. Hiking trails become eroded, creating gullies and accelerating soil loss. Popular peaks become crowded, with climbers sometimes waiting in lines to reach summits. Waste accumulates, from discarded gear to human waste. Finding ways to allow people to experience mountains while minimizing environmental impact is an ongoing challenge. Mining continues to be important in many mountain regions, providing valuable minerals, but also creating environmental disturbance. Modern mining can remove entire mountaintops, completely changing the landscape. Careful regulation and reclamation can minimize impacts, but mining inevitably changes landscapes, at least locally. Balancing economic needs with environmental protection requires thoughtful management and respect for mountain ecosystems. Let's pause for a moment and consider what all this means. Mountains have existed for billions of years and will continue to exist for billions more, but they're not unchanging. The specific mountain ranges we know today will eventually be eroded away and replaced by new mountains in new locations. The ice and snow we associate with high mountains might become less common as climate warms. The ecosystems that currently inhabit mountains will change, with some species lost and new assemblages forming. Yet despite all these changes, mountains will remain. Earth's interior will stay hot for billions of years. Scientists estimate that Earth's interior will remain hot enough to drive plate tectonics for another billion years or more. Convection currents will continue to churn in the mantle. Plates will move, collide, separate. And where plates meet, mountains will rise. The specifics will change, but the process will continue. Earth will keep building mountains because Earth has the internal heat and dynamics to do so. There's something both sad and hopeful about this long view. Sad because the mountains we know and love today won't last forever. The Himalayas will eventually be worn down. The Alps will be reduced to hills. Even Mount Everest, currently the highest point on Earth's surface, will someday be just a memory preserved in sedimentary rocks. But hopeful because the process continues. New mountains will form. Earth will keep reshaping itself. The planet remains active, dynamic, alive in a geological sense. For humans, the challenge is to live with mountains in ways that don't destroy what makes them special. To enjoy mountain landscapes without loving them to death. To use mountain resources without degrading mountain ecosystems. To understand that mountains, despite their apparent permanence, are vulnerable to human impacts, especially rapid climate change. We've learned so much about how mountains form, how they work, how they shape climate and ecology. Now we need to apply that knowledge to protect these spectacular landscapes. So the future of mountains is uncertain in details, but certain in broad outline. Mountains will continue to rise and erode. The dance between tectonic forces and erosion will continue. The specific configurations will change, but mountains as a feature of Earth's surface will persist as long as plate tectonics operates. And as long as there are mountains, there will be people who look at them with wonder, who climb them, study them, live among them, and find meaning in their presence. Closing sequence. What are mountains? It's the question that brought us here, whispered softly at the beginning like a child asking if rocks can grow tall enough to touch the sky. And after wandering through tectonic plates and volcanic eruptions, through folding and faulting, through geological time and mountain ecosystems, we find ourselves gently circling back to where we began, still wondering, still awed. We've learned that mountains are born from the restless energy of Earth's interior, from convection currents that move continents and push the crust upward. We've explored how plates collide, continental with continental creating the Himalayas, oceanic with continental building the Andes. We've seen how subduction creates volcanic mountain ranges and how hotspots punch through plates to create island chains like Hawaii. We've discovered how rock responds to enormous forces, folding into graceful curves or breaking along faults. We've learned about isostasy, how mountains float on the mantle like icebergs on water, supported by thick crustal roots. We've seen how erosion and uplift work together, how the wearing down of mountains paradoxically helps maintain their height through isostatic rebound. We've explored the role of water and ice in sculpting mountains, how glaciers carve U-shaped valleys, and how rivers slowly cut through the hardest rock. We've examined different types of mountains: fold mountains, fault block mountains, volcanic mountains, each with its own origin story. We've contemplated geological time, those vast expanses of millions and billions of years over which mountains rise and fall. We've seen how mountains create unique ecosystems, how life adapts to thin air and cold temperatures, how mountains influence climate far beyond their own slopes. We've explored the relationship between humans and mountains, seeing how mountains have shaped human culture, history, and imagination. And we've looked toward the future, recognizing that while specific mountain ranges come and go, the process of mountain building will continue. Maybe mountains don't have to be permanent to be meaningful. Maybe that's the whole point. The universe doesn't stand still. Earth doesn't stand still. Everything changes, even mountains, though they change so slowly that they seem eternal from our brief perspective. And perhaps there's something beautiful about that impermanence, about the patient rise and slow wearing away, the endless cycle of creation and destruction that has shaped our planet for billions of years. Mountains teach us patience. They remind us that even the mightiest changes happen slowly, steadily, grain by grain, millimeter by millimeter. They show us that persistence, not speed, is what shapes the world. They invite us to think on timescales beyond our normal experience, to see our planet not as a static backdrop, but as a dynamic system, constantly in motion, constantly being renewed. So, with all of this in mind, are you still awake? If you are, I hope it's not because I was too interesting. Though if I was, well, at least you've learned a few things about the slow, powerful heartbeat of our planet, about how the mountains that seem so solid and permanent are actually flowing, rising, changing, just too slowly for us to see. And if you're already halfway to sleep, may your thoughts be filled with softly folding rocks and gently rising peaks, with volcanoes quietly building their cones and glaciers slowly carving their valleys. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Drop a comment and share. Are you perhaps in the shadow of mountains yourself, or listening from flat plains and wondering what mountains might be like? Are you a geology student, or someone who just finds the patient work of tectonic plates strangely soothing? If you found this gentle journey into mountain formation relaxing or informative, or both, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture that helps me keep bringing you more calming, curious content about our fascinating planet and beyond. Your support means the world to me, or at least a small mountain's worth. Thank you for joining me on this journey through the world of mountains. Sleep well, dream deep, and may your thoughts drift peacefully like tectonic plates, slow and steady, reshaping themselves over time. Remember, mountains teach us patience. They remind us that even the mightiest changes happen slowly, gently, millimeter by millimeter, year after year. As you rest, perhaps you'll dream of India drifting northward across an ancient ocean, approaching Asia at the speed of growing fingernails. Perhaps you'll dream of lava flowing gently down a Hawaiian volcano, adding new land to the Big Island. Perhaps you'll dream of rock layers folding like fabric, bending into elegant curves under forces too vast to comprehend, but too slow to see. And perhaps, as you drift towards sleep, you'll remember that somewhere on Earth right now, mountains are rising. Imperceptibly slowly, invisible to any observer, but rising nonetheless. The Himalayas grow by 4 millimeters this year, the Andes by 3. Somewhere a volcano adds new rock to its flanks. Somewhere a glacier carves deeper into its valley. The patient work of mountain building continues, as it has for billions of years, as it will for billions more. Good night.